Hey guys, let's talk about the second order reaction kinetics. Now, in this video, we are going to talk about the integrated rate law, and then we are going to talk about the half-life of a second order reaction kinetics, or of a second order reaction. Now, talking about the integrated rate law, before now, we know that the half-life, the rate equation for a second order reaction can be given as K, then the concentration of A square. K is equal to the concentration of A square. Now, if rate is equal to K times the concentration of A square, we also know that rate can also be written as dA all over dt. Of course, you put the negative sign here to show that there is a decrease in the concentration of A as time progresses during the course of the reaction. Now, since the rate law here is equal to the rate law here, what are we going to do? Or since the rate here is equal to the rate here, what are we going to do? We are going to equate these two equations. So at the end of the day, what are you going to have? You are going to have K, then A square is equal to minus dA all over dt. Now, this equation, the way it is, we can rearrange it in such a way that we are going to have minus dA all over dt is equal to K, then A square. Now, minus dA all over dt is equal to K A square. At this point in time, you say this is over 1. Now, let us make all the A's come to one side, and then K and dt go to the other side, so that we can easily integrate. And this will give you minus dA is equal to K A square times dt if you cross multiply. Now, divide both sides by A square. Divide both sides by A square. A square cancels A square. We have minus dA all over A square. This is equal to K dt. Now, if you multiply both sides by minus here, the minus sign is going to leave here and come here. And then if you integrate, this is going to give us the integral of... Now, while you are integrating, you integrate in such a way that this dA will come out, and then it will now be the integral of 1 over A dA as change in A. So this will be 1 all over A square and then dA. Now, the reason why we placed it like that is because most integral, for instance, you must have something like m with respect to what? M. Are you getting it now? So that is why we have to bring it. So integrate 1 over A square with respect to dA. Now, this will be equal to minus, of course, we know our minus K will come out because it's a constant, and then we have the integral of dt. Now, when you integrate this, what is it going to give to you? Now, do you agree with me that 1 all over x is still the same thing as x raised to the power of 1? Therefore, 1 all over A square is equal to A raised to the power of minus 2. Since 1 all over S square is equals to x raised to the power of minus 2. Now, if we substitute that into this equation, let's go to a fresh page so that it will be very easy for us. If we go to a fresh page, this is going to give us integral 1 all over A square dA is equal to minus K integral of dt. Of course, we know integral of dt, upper limit of t and lower limit of t, which is what? 0. This will give us, everything here will give us minus K integral of the t is t. And then this is upper limit t, lower limit is 0. So even if you do t raised to the power of t minus t raised to the power of 0, this will be t, because wherever you see t here, you put t, minus t. Wherever you see t here, you put 0, minus 0, and this will give us t. So this whole stuff here will sum up to give us t, and this is minus kt because of this negative here. Now, having gotten this, what are we going to get for the integral of this? I said the integral of this will be the same thing as integral of a minus 2 dA, which equals to minus k dt. Now, if you integrate this, it's going to give us, now, minus a raised to the power of minus 2. If you integrate, you add 1 to the power and divide by what you have here, which is minus 2 plus 1. And this will give us a raised to the power of minus 2 plus 1 is minus 1. Minus 2 plus 1 is minus 1. And this will give us a raised to the power of minus 1 divided by minus 1. And finally, this is going to give us, if this minus 1 comes up, it becomes minus a raised to the power of minus 1. Now, if you integrate, or if you, anything raised to the power of minus 1 is the same thing as 1 all over that thing, right? So this will be minus 1 times 1 all over a. So in place of this, minus 1 times 1 is, so this is minus 1 all over a. And that is the integral of everything we have here. So we can say this is equal to, now when you are integrating, know that you are integrating the upper limit, which is AO, all over, or let's say the final AT, then the lower limit AO. And then at the end of the day, you are going to have minus 1 all over. We are putting minus 1 all over a in place of this whole integral of this stuff here. And this will give us raised to the power of, divided by a. Then we, of course, have the upper limit, which is AT, and the lower limit, which is AO. And of course, this is equals to minus KT. Now, what does this mean? It means you have minus 1 all over A raised to the power of AT. Then minus, we have another one. Now, of course, you know there is a negative here, right? So I can decide to put minus here, and then here, minus divided by, and then here is also minus 1 all over A raised to the power of AO, which is the initial concentration. Now, AT is the concentration at the particular time, and AO is the initial concentration. So at the end of the day, when you put AT in place of A here, this becomes, let me wipe this off. So when you put this in place of A, this becomes minus 1 all over AT, then minus. Now, in place of A here, what are you going to put? You are going to put AO, because that is what is on top here. And this becomes minus 1 all over AO. And then at the end of the day, you are going to have minus 1 all over AT, because you know this AT, then minus times minus will give us positive. Then you have 1 all over AO. Everything here is equal to minus KT. Now, let us assume the initial concentration, or let us do something here. This is minus. If we rearrange this equation, if we make AO, which is positive, to come here, this becomes 1 all over what? AO minus 1 all over AT. Now, AO is equal to initial concentration. And then AT is equal to the concentration at the time, which we can say is the final concentration. Now, how about if we make Instead of writing AO and AT, how about if you make a prediction and say, let me put this at this small space here. Now, if we can say, let this AO, which the initial concentration, be equals to A, and then after some time, let us say X amount of the ingredient or X amount of the drug degraded or decomposed. Now, this to say, to find the concentration at that particular time, it will be what? A minus S. Because we said at a particular time, X amount of the concentration has what? Degraded. So what is remaining at that time will be A minus S, because S has given up. So in place of AO, initial concentration is A, then AT is equals to A minus X. So substituting into this equation, of course, you know this is equals to minus KT. This will be equals to 1 all over A minus 1 all over A minus S is equals to minus KT. And then when you find the LCM of this and this is A bracket A minus X, A divided by A will give us A minus X remaining. Then A divided by A here will give us minus A remaining. Is that not so? Because this A minus S cancels A minus S, so you are left with what? A. A times 1 is minus A. This is equals to minus KT. Now if we go to a fresh page, what we had here initially is, let me rewrite, is A minus X minus A all over A bracket A minus X is equal to minus KT. I believe that is what we had there. Okay. Now, do you know that this A minus A will give us 0? So what we are left with here is X, because this A cancels this A. So we have minus X all over A bracket A minus X. Everything is equals to minus KT. Now, do you know that this negative here, we can place it here in such a way that this negative cancels this negative. So our X is A bracket A minus X, and this is equal to KT. So this is the formula for the second order rate law, the integrated rate law for the second order kinetics, okay, or for the second order reaction kinetics. Now, have we gotten KT as equal to S all over A bracket A minus S? So we can say that our KT is equal to X all over A bracket A minus X. Now, how do we make T subject to the formula? We said T will not be equal to X divided by, or we want to make K subject to the formula. Let K stand on its own. So K will be equals to divide both sides by what? T. And this becomes A bracket A minus S times T. Now, have we gotten K and KT? Let us calculate for the half-life. What is the half-life? We said the half-life, which is T raised to the T subscript half, is the time it takes for the substance to degrade to half of its initial concentration. It means our change in T, or our final concentration, will be half of the initial concentration. So in that case, what do you think will be our half-life for this reaction? Now, if you go back to what we solved initially, you will discover that we said 1 all over A O minus 1 all over AT is equal to minus KT. We did something like this. Now, have we gotten this? We now know that our AT is equal to half of AO. So in place of AT, we put half of AO. And this will be equals to 1 all over AO minus 1 all over AT. In place of AT, we put 1 over 2 AO. And this is equals to minus KT. And then we'll have 1 all over AO minus 1 all over, this times this is AO all over 2 is equal to minus KT. Now 1 all over this, all over this. Of course, you know when you are finding the inverse of anything, this whole thing here will sum up to be 2 all over AO is equal to minus KT half. You must indicate the half to tell us that you are talking about the half-life. Now when this 2, where's the LCM of AO and AO? Of course it's AO. All over AO divide AO is 1 times this is 1. AO divide this is 1 times this is 2 is equals to minus KT half. And then when this minus this is going to give us minus 1 all over 2. Or sorry, what is that? Come here. This will be equals to minus 1 all over AO is equals to minus KT half. This minus can cancel this minus. Now recall that we said let our initial concentration AO be equals to A. So wherever we see AO, we put A. And this becomes 1 all over A is equals to KT subscript half. Now to find T, divide both sides by K. And when this cancels this, our T subscript half is 1 all over AK. And this is the formula for the half-life of a second order reaction. Please take note of these formulas because you are going to use them to solve, especially this to calculate the rate constant and then this to calculate the half-life. Now this is for the constant for second order reaction and this is for the half-life. Now let us use this ideology now to solve this question. The question says consider the reaction between acetic anhydride and sodium hydroxide in a bimolecular reaction. Now if the concentration of acetic anhydride and sodium hydroxide in the mixture were, now it means that their initial concentration were the same and that initial concentration has a value of 0.075 mole. The change in concentration of sodium hydroxide during the 30 minutes. So the time was given as 30 minutes. So we are working with minutes now. Now, if the change was, it means our X is 0.045 molar. Calculate the rate constant and then the half-life. Now, what is the rate constant? We say the rate constant K is X all over A bracket A minus S bracket T, where S is the change in concentration. Okay, so our K now would be equal to, where's our S here? 0.045 divided by, where's our A? Initial concentration is 0.075 bracket 0.075 A minus 0.045, and then your K would be equal to, what would that give to us? That would give us 0.075 minus 0.045, and this will give us 0.03. So this gives us 0.45 divided by 0.075 times 0.03, and then your K be equals to 0.45 divided by this times 0.075, and that will give us 0.00225. okay, 0.075 times 0.03, 0.00225. Now K would be equal to 0.45 divided by 0.45 or 0.045. 0.045. This is also 0.045. So when you press this your calculator, 0.045 divided by 0.0025, that will give us 18. So our K is equals to 18. Now what is the unit for second order rate law? I believe we know the unit before now. The unit is equal to liters per mole per second. So this is equal to liter per mole per minute, because the time given to us was 30 minutes. Now, finding K, we didn't multiply by T. So we need to multiply here by T. Here is 30 minutes, okay, which is our T. So we need to multiply everything by T here by 30. So we need to divide this, anything we got here, by 30. And that will give us the expected answer. Sorry for that omission. 0.0, that is 0. Let me start from under. 0.075 times 0.03. This times 30, which is 0.0675. So everything here will give us 0.0675. Now, when you divide up and down, this 0.045 divided by 0.0675, and that will give us 0.666, which is 0.67 liters per mole per minute. And that is the rate law for that, or the rate constant for that particular question. Now, what will be the next? The next question is the half-life. What do you think the half-life would be? Sorry. The half-life is T half is equal to 1 all over A K. So your constant now will give you the value for the half-life, which is this, is equal to 1 all over. What is initial concentration? 0.075 times K is 0.67 per minute. And then at the end of the day, 0.67 liter per mole per minute. Okay. Now, of course, this one is mole per liter times 0.67 liter per mole per minute. Okay. So liter cancel liter, mole cancels mole. And then your half-life would be equal to 1 divided by, now 0.075 times 0.67. That will give us 1 divided by 0.05025. And then 1 divided by this. 1 divided by this is equal to 19.90, which is our half-life is equal to 19.90 minutes, which is approximately 20 minutes. Okay, so this is the half-life of this reaction, and this is an exam question, so please take note of it. It may repeat itself again, we never can tell. Now let us check if we made any error in this calculation. If everything is okay, then we may proceed to the next. But let's check if we make any error. If we made any error, our S is 0.045 is correct. Our A is 0.075, that is correct. Then this becomes 0.075 minus 0.045, and that is correct. Then bracket 30 minutes, which is our time, and that is correct. Then when you substitute in, everything gives you 0.045 divided by this 0.075 minus 0.045. That will give us 0.03 times 0.075 again. Then times 30. That will give us 0.0675. Then 0.045 divided by the answer, which is 0.067. Okay, it's very correct. Then when we came here, this gave us this. It's very correct. This is our A, initial concentration, and this is the value for K, and the answer gave you 20 minutes. So that is all for second order rate law. Thank you for your time. And please make sure that you subscribe. subscribe to this channel. It's very important to subscribe. Okay, share, click the share button, and also comment below if there is any confused place for you to be explained, or any confused place you need more explanation. Thank you.